Now that we've seen how to differentiate inverse trig functions, in this lesson we'll do the opposite process, which is to spot the results of those differentiations and integrate to get back to inverse trig functions. Notice that we're not actually integrating an inverse trig function in this case, and that's because we get purely algebraic functions when we differentiate inverse trig. So we need to look out for those algebraic functions that don't contain sine, cos or tan. They really just have x's and other functions in them, and generate the results which are inverse trig functions. Now I've written these three basic forms down here because we've already seen that if you differentiate this, then you get this. So if we integrate it, we'll get back to where we started, but we need to add a constant for integration. And we've got the same here. Now this one is not strictly necessary. I want you to have a think about why it isn't. If we have a negative out here, couldn't we also have said, well, that's the same thing as putting the negative out the front, and then what we'd really have here is just negative inverse sine of that function plus c. So really, we don't need to deal with this one because we could actually just use this and this to cover everything. So, I mean, ideally, you could say here, look, this is also negative inverse cos, but so what? If you are integrating something and you get yourself a result, it doesn't need to have a bunch of different forms, and we don't need all of this variety. So what you'll see is that on your reference sheet, we only get this version and this version, but this is not how they're written on your reference sheet. And the reason they're not written this way is that this is sort of like your perfect question, which has got the 1 down the bottom here in the denominator. And I've written here, but what if you had a number other than 1 in the denominator? What would you do? Well, we need a version of these formulas that actually accounts for having another number down there. Now this proof has a step in it that you'll probably feel is a little bit tricky. It's something that you'll be able to understand when I do it, but you might not have thought to do it yourself. You don't need to be able to reproduce this proof in an exam setting, but you should be able to follow along with what I've done so that when you're using the formulas that are on your reference sheet, you've got an idea where they came from and you're not just taking my word for it that they work. So, okay, we've got here what looks very familiar. It looks like it's going to be the inverse sine of x because the thing that we've squared here is just x. It's a very simple function of x. But the thing that's getting in the way is this a squared when we're used to seeing only a 1 there. So what we're going to do is just manipulate this expression, make it look different. So I'm going to start by taking everything that's in the denominator and factorising what's inside the square root part. Now, why am I factorising? Well, one of the main purposes of factorising is that it can turn a plus and minus situation where here I've got two terms, one taken away from the other, and I can't do much to separate them out and take the square root of them separately. Whereas, don't forget this rule, if I'm taking the square root of two things that are multiplied together instead of added or subtracted, then I can take the square root of each one separately and then multiply them. I can't do that here. So I want to factorise literally just so I've got a multiplication situation going on here underneath my square root bracket. So I've brought a squared out the front because that seems a logical thing to do, and that will leave me with 1 minus x squared over a squared underneath. Okay, on the next line, I can do exactly this. I can say, let's take the square root of a squared, that'll just be a, so I can put that separately. Actually, let's keep it together, but we'll put the a there on its own, and then we have the square root of just this section. And let's tidy it up a little while we're here and call it x over a, all squared, like that. Okay, now the next step is not completely intuitive. You might not have thought to do this, but if we let u equal this part that's been squared here, the x over a, then we can do something a little bit tricky and say du dx, and remember this is really just 1 over a multiplied by x. When we differentiate with respect to x, we get 1 over a. Now we can use that result in here. How are we going to use it? Well, we've got 1 over a here. So if I just rearrange this and say, let's put 1 over all this complicated part, and we'll call this u squared now because we're sort of tidying up. And now we're going to multiply that by 1 over a dx. Can you see what I've done there? I've just split the fraction. I've put the 1 over a separately, I've put this bit separately, and I've called that u. I can now say, hey, I've got an expression here for 1 over a. It's equal to du dx. So subbing that in on the next line, I have this, and then I have du dx, because that's equal to 1 over a, and then I've got my dx. Now, can you see here that even though this isn't actually a fraction, we're a bit cheeky and we use it like a fraction a lot of the time in maths, and the dx's here are actually going to cancel. So now what we have is much more familiar. It's got the 1 there, and we are literally going to integrate with respect to u. We don't even really need that multiplication sign there because we don't normally actually write that. But effectively, we're now integrating here with respect to u. So what we can say is that we get the inverse sign of u plus c. Now, of course, we shouldn't put the u into our answer. We know that u is actually x over a. So let's replace that at this point. And now we have a rule. Now, the proof for the other form involving the inverse tan of a function is similar, but just slightly different. We'll go through that as well. So similarly here, I want to adjust this formula so that I get the a squared on its own or sort of away from this. So if I change this so that I have a squared out the front of some brackets, I end up with a very similar looking thing on the bottom here. We just don't have the square root. And similarly, I can let u equal x over a, and then du dx is again equal to 1 over a. And summing that in over here, you'll see that what I have is 1 over a squared, not 1 over a, all right? But if a is actually a constant, then what we can do is we can separate this into sort of 3 parts, I suppose. We've got 1 over a, we've got another 1 over a, and then we've got our main part, which now looks much more familiar. In fact, let's call that u squared dx. So we have all of that. And the trick that we're going to use is we'll bring one of these 1 over a's out the front of the integral, which you can always do with a constant. Now, the beauty of that is that we end up with the 1 over a out there. We can sub in the 1 over a for du dx again. So we end up with this, just pushing this part down here, and then we have our du dx and our dx. Again, the dx's cancel, and now we can integrate this part with respect to u, but our 1 over a still stays floating out the front. So what we end up with is the inverse tan of u, where u is x over a, so we have x over a like that, plus c. Now you might have noticed that in both of those proofs, we used a really simple function of x, just x itself. So our proofs didn't have the f dash x part on the top, but we've already seen how to deal with that in our previous integration and differentiation. And so now we can see that these are the 2 forms that are actually on your reference sheet. They include the f dash x up the top, and we can see they've both got a squared in them. And the main difference, we can see that we get that 1 over a floating out the front of the inverse tan one. We also can see why we don't need a result involving inverse cos, because of course, if we get something that looks exactly like this, a perfect question, then we can go ahead and just reproduce the results here straight off our reference sheet. But if our question isn't perfect, for example, if it had a negative f dash x out the front here, then we can always account for that by saying we've got the negative inverse sign. We don't have to call it inverse cos, although it wouldn't be wrong if we did.